Now for order 3, if it is stable, I am giving one shortcut method if you understand or not. Internal quotient product should be greater than the external quotient product and the constant should be greater than 0. If these two conditions are satisfied, directly the closed loop control system is stable. Then I will take another example. Now see here, this is s cube plus 3s square plus 4s plus 100 equal to 0. So here is also I am giving one shortcut method first, then after that we will go for the general method. Now the internal quotient product. The internal quotient product 3 into 4 is 12. External quotient product 1 into 100 is 100. Now here the internal quotient product is less than the external quotient product. Now the closed loop control system is directly unstable. Now there is no second condition, nothing, direct shortcut method. Internal quotient product is less than the external quotient product, system is unstable. But you have some confusion, no? Then we go for the general procedure also. What is the general procedure? The highest power is s power 3. Now the highest power is s power 3 is an odd power, right? All the odd power quotients 1, 4, 0. Now s square even power, write the even power quotients 3, 100, 0. Now s cube, s square and s power 1, 3 into 4, 12, 12 minus 100, so minus 88 by 3, 3 into 4, 12, 12 minus 100, 12 minus 100, minus 88 by 3. Now 3 into 0, 0, 0. Now x into 100, this is assume x, x into 100, 100x minus 0 by x, this is 100, 0, 0. This is s power 0. Now see here, now this is the first column, now this is the first column. Now positive, positive, negative, positive. Now sign is changing or not? Whenever the sign is changes, system is unstable. If any sign change, closed loop control system is unstable. And what the shortcut method is saying? The shortcut method is saying that internal quotient part is less than, system is unstable. Now you check general method, how many sign changes? Now this is plus 3. Positive to negative, 1 sign change. Now negative to positive, this is the another sign change. Total how many sign changes? 2 sign changes. 2 sign changes, which will give 2 closed loop poles. 2 closed loop poles lies on right hand side of S plane. 2 closed loop poles lies on right hand side of S plane. This is with the shortcut method, with the long method will give the same result. Now from the next time onwards for order 3, don't use this lengthy method, use that shortcut method, you can get the answer directly, no doubt. Okay. Now in the order 3, then you have a shortcut method, and I am giving one more question also. S cube plus 3s square plus 7s plus 21 equal to 0. Now if you see here, this is characteristic equation of order 3. The internal quotient product 3 into 7, which is equal to 21. The external quotient product 1 into 21. The external quotient product 1 into 21, which is equal to 21. The internal quotient product is equal to the external quotient product. If the internal quotient product is equal to the external quotient product, closed loop control system is marginally stable. If the internal quotient product is equal to the external quotient product, closed loop control system is marginally stable. Understand or not? So this is the shortcut method. But sir, then you show me this is in the general method. Okay, I will tell you that is in the general method also. Okay. Now see here, this is the characteristic equation as cube plus bs square plus cs plus d is equal to 0. As cube plus bs square plus cs plus d equal to 0. Now this is a is greater than 0 and b is greater than 0. This is the condition. Okay. Now you first find the tabular form. Now s cube is an odd power. Now write all the odd power quotients. All the odd power quotients is a, c, 0. S square is an even power. Write the even power quotients b, d, 0. Now s power 1 bc minus ad by b 0, 0. S power 0, this is x, d into x minus 0 by x, this is d 0, 0. Then if you see here, this is the first column. This is the first column. If the closed loop control system is stable, 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 all the quotient in the first column should have same sign. A is positive already in the condition is given. So there is no other choice. B must be positive. Yes, B is greater than 0. So this fellow you should be maintaining positive. What is that fellow? BC minus AD by B is greater than 0, such that what is the condition? The condition is BC is greater than AD. The students, if you observe or not, what is BC? This BC is nothing but the internal quotient product. What is AD? The AD is nothing but external quotient product. What I am saying previous questions earlier, shortcut method. BC, internal quotient product, is greater than the external quotient product such that the system is stable. That is the shortcut method which is given by RH only. And one more thing, positive, positive, A is positive, B is positive, this condition is positive now, and the D must be positive for that. Okay. So that's why I am giving another condition. Now the D constant must be greater than 0. If these two conditions are satisfied in order 3, then the closed loop control system is directly stable without doing the tabular form and all these things. Okay. Now similarly, now when the closed loop control system is unstable, if the system to be unstable, at least one sign change is required. At least one sign change is sufficient to maintain the system instability. Now A is positive. This is a positive fellow. B is positive. B greater than 0. Positive, positive. Can I make this is negative? How you can make this is negative? So you can make that is negative. BC minus AD by B is less than 0. Therefore, now the condition BC is less than AD. The internal quotient product, again, the internal quotient product is less than the external quotient product. Closed loop control system is unstable. Is matching or not? Okay. Now one more condition. if the closed loop control system, this is the shortcut methods we are following, right? Okay. If the closed loop control system is marginally stable, if the closed loop control system is marginally stable, if the closed loop control system is marginally stable, one condition in the tabular form, one complete row, one complete row becomes 0 in the RH tabular form. One complete row becomes 0 in the one complete row becomes 0 in the RH tabular form, such that the closed loop control system is marginally stable. That is the reason why, if you see here, then you ask, sir, why one complete row equal to 0? What is the meaning of complete row? If complete row becomes 0, what happens, sir? That we will see. Okay, why? What is the reason behind that? Now, what is the meaning of row becomes 0? When the situation, the row is demanding 0, what is the meaning if the row is 0? Now, that also I will tell you. Okay, so when the system is marginally stable, one complete row becomes 0 in the RH tabular form. So if you make one complete row become 0, if I make it A equals 0, this row is 0? No. If I make it B is 0, this row is 0? No. But if I make this BC minus AD by B equals 0, if BC minus AD by B is equal to 0, then you can get a complete row becomes 0. Now 1, 2, 3. The third row will become 0 now. Third row is completely 0. The third row is completely 0 now. Okay. Now what is saying? When if BC minus AD by B0, one complete row becomes 0 such that the system is marginally stable. Now BC minus AD by B equals 0. So BC is equal to AD. That is the reason why I am saying, if the system is marginally stable, see the students, if the system is marginally stable, the internal quotient product BC, external quotient product AD is equal. The internal quotient product is equal to external quotient product. Now the system is marginally stable. These are the three situations for order 3. Now next time you don't do all these things, you do directly these shortcut methods and you can get all the 3 cases. Okay, note down neatly. Okay. Now the students, if order is 3, okay, use this shortcut method directly and you can get the answer. But the third point we will get the clarification, full clarification. Okay. If order is 3 and your problems are very easy because you have some shortcut methods, use that shortcut method directly and make the system is stable or unstable or marginally stable easily. Now we'll solve one by one question, now increasing the orders. Okay. Now this is fourth order. Now this is the characteristic equation of order 4. Now this is the characteristic equation s power 4 . This is the characteristic equation of order 4. Now even power. Now write all the even power quotients. 1, 3, 5. S cube. Odd power. Write all the odd power quotients. 2, 4, 0. Now s square. 2 into 3, 6 minus 4, 2 by 2, 1. 2 into 5, 10, 10 minus 0, 10, 10 by 2, 5, 0. Now s power 1, what is s power 1? 1 into 4, 4, 4 minus 10, minus 6. 1 into 0, 0, 2 into 0, 0, 0. S power 0. Minus 6 into 5, minus 30, minus 0, minus 30 by minus 6, 5. Now see, this is the first column. This is the first column. Now in the first column, there is a sign changes. Positive, positive, positive. But this is negative, this is positive. Now any sign changes in the first column, you know that the closed loop control system is unstable because at least one sign change system is unstable. How many sign changes? Positive to negative, one sign change. Negative to positive, another sign change. Therefore, two sign changes. Therefore, two closed loop poles lies on right hand side of S plane. Two sign changes, therefore two closed loop poles lies on right hand side of S plane. There are two sign changes, therefore two closed loop poles lies on right hand side of S plane. System is unstable. Okay. Now this is for order 4. Note on this. Okay. Now this is the characteristic equation of order 4. This is the characteristic equation of order 4. S power 4 is an even power. Write all the even power quotients. 1, 2, 8. S cube, odd power. Write all the odd power quotients. 2, 4, 0. Now even power quotients and odd power quotients. Next, s square. Now 2 into 2, 4 minus 4, 0 by 2, 0. 2 into 8, 16. 16 minus 0, 16 by 2, 8, 0. Now see here. Now the condition 2 is failed. What is the condition 2? The first column quotient should not be 0. Am I right? Not. What is the condition 2? The first column quotient should not be 0, not equal 0, not equal 0. But this is the one of the first column quotient is 0. Now if one of the first column quotient is 0, sir, what happens, sir? If you continue, now what happens? What is the next? 0 into 4, 0, minus 16 by 0, and you can get infinity. And if you continue infinity by infinity, an undeterministic state will be coming. So therefore, then any one of the first column quotient should not be 0. All the quotient in the first column is not equal to 0. Now, if one of the quotient in the first column is 0, so we have to find such any other alternate solution. If any one of the first column quotient is 0, replace that 0 with a smallest possible positive constant epsilon. Replace that 0 by a smallest possible positive constant epsilon and continue the tabular form. Okay. If any one of the first column quotient is 0, replace that 0 with a smallest possible positive constant epsilon and continue the RH tabular form. S power 1 epsilon into 4, 4 epsilon minus 8 into 2, 16 by epsilon. Next, epsilon into 0, 2 into 0, 0, 0. Now s power 0, assume this is some x, x into 8, 8x minus 0 by x, therefore this is 8. Now all the first column quotient, the sign say same sign or not? This is positive. This is positive. This is positive epsilon. But this is positive or not, we don't know. This is a function of epsilon. Therefore, while deciding the system stability from the first column, again you replace epsilon with 0. Right? Epsilon with 0 and find that should be a positive value or a negative value. 4 epsilon minus 16 by epsilon, and identify this should be a positive value or negative value by replace epsilon with 0. Epsilon tends to 0. Therefore, which is nothing but 4 minus 16 by epsilon, and if I take epsilon as a common here, epsilon cancel and epsilon tends to 0. Therefore, which is nothing but 4 minus something by 0, infinity, 4 minus infinity. Therefore, this is minus infinity. Now, this is the negative sign. This is the negative value. This is a minus. Now, see here, positive, 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 but this is the negative. Sign is changing. If any sign changes, system is unstable. Closed loop control system is unstable. How many sign changes? This is positive to negative, one sign change. Negative to positive, and this is another sign change. Therefore, two sign changes for two closed loop poles lies on right hand side of S plane. So now if the condition 2 is failed, you know how to overcome. If any one of the quotient in the first column is 0, replace that 0 with the smallest possible positive constant epsilon, continue the tabular form. Now after completion, again replace epsilon with 0 and identify that is a positive sign or a negative sign. This is a procedure when the condition 2 is failed. No doubt. Clear or not? Now this is the characteristic equation. This is the characteristic equation of order 5. This is the characteristic equation of order 5. Then now you see here, this is s power 5, odd power. Write all the odd power quotients. 1, 3, 2. Now s power 4, even power. Write all the even power quotients. 1, 3, 2. Now the third row is s power 3. 1 into 3, 3 minus 3, 0. 2 minus 2, 0, 0. Now what happened now? See the students here. Now one complete row become 0. Am I right? Now one complete row will become 0 here. Now you already know that any RH tabular form, one complete row will become 0 such that the system is marginally stable. But there we just remember system is marginally stable. Now here we will see the reason behind why it is marginally stable. What is the meaning of row becomes 0? Now the question is, sir, when the row will become 0, in which situation the complete row will become 0? Now in such a situation, what happening? Okay, now I will try to explain that. Now let us take this is and explain. Now this is one pole. Let us assume this is at -1. Now one pole is at -1 and there should be a symmetrical pole is at +1. Now what is the magnitude of this one? 1. Square root of real part square plus imaginary part square. Therefore magnitude is 1. What is the magnitude of this one? Square root of real part square plus imaginary part square. Therefore magnitude is 1. Therefore this magnitude is 1. This magnitude is 1. Then these two magnitudes are same because these two poles are arranged symmetrical. When the magnitudes are same, there may be a chance of cancellation. 1 minus 1 will become 0. Now in the same manner, one pole is at -2, one pole is at -3, one pole is at -2 and one pole is at -3, and there exists a symmetrical pole at +2 and at +3, and there should be a symmetrical pole at +2 and +3, and these magnitudes and these magnitudes are same. When the magnitudes are same, then 2, 3, 2, 3, and there may be a chance of cancellation and the row will become 0. Now one pole is at +J1, one pole is at +J2, another pole is at -J1 and another pole is at -J2. Now see here. Now these poles are on imaginary axis with respect to origin, and this is also how these are arrangement, symmetrical arrangement. So whenever the symmetrical arrangement, magnitude is 1, 1, 2, 2. So whenever the poles are arranged symmetrical, then there is a chance of cancellation because magnitudes are same. Then there is a chance of cancellation and there is a scope of this row will become 0. Therefore, the first reason behind one complete row becomes 0 is, can write here. First point is symmetrical poles. Symmetrical poles with respect to origin. Symmetrical poles with respect to origin. If the poles are arranged symmetrical with respect to origin. And the second point is, if the symmetrical pole, how many are the total number of poles here? 2. Here 4. Here 4. Which means that if you want the poles are arranged symmetrical on the S-plane, the poles must be even in number. And second one is even number of poles. Even number of poles. So the reason behind the symmetrical arrangement is only the even number of poles. Even number of poles are only a chance of arranging symmetrical, such that even number of poles, there may be a chance of symmetrical, means magnitude will be same, then there may be a chance of cancellation and the net result will become rho become 0. Okay. In such a situation, then there may be a chance of one complete row become 0. So in the previous question, only one column, one of the quotient in the column is 0. In the previous question, if one of the quotient in the first column is 0, I am unable to solve that particular tabular form such that I want to search any alternate solution. But here one complete row will become 0, and how can I continue the tabular form? We have to search a method. Now you know the reason behind this row becomes 0. This is totally because of even number of poles. This is totally because of even number of poles, such that now ask the help of even number of poles and try to simplify this particular question. So even number of poles, therefore the reason behind the even number of poles, and you already know that whatever you want to do it in this particular row, who is responsible for that particular row? The top of the row is responsible for that particular row. Therefore this is the auxiliary equation. What is auxiliary equation? This is the auxiliary equation, s power 4 plus 3s square plus 2 into s power 0. This is the auxiliary equation. And one important point here, the auxiliary equation must be even power of s term, because only the even number of poles will have this type of situation. Therefore this is the third point. The third point is the auxiliary equation. The auxiliary equation must be even powers of s terms. The auxiliary equation must be even powers of s terms. Understand or not? So even power of s terms. Now the auxiliary equation must be even power. Why? Because why even power? Even power, then even number of poles. Even number of poles, there is a chance of arranging symmetrical with respect to origin and cancellation, and the row will become 0. So you replace the row of zeros with some quotient by taking the help of auxiliary equation. The auxiliary equation is already even power, but you want to replace the quotient is in the odd power. Therefore you differentiate this auxiliary equation, you can get a even powers, right? So if you differentiate this, dA by ds is equal to 0. If you differentiate, what happens now? Now 4s cube plus 6s plus 0 is equal to 0. Now you replace the quotients with the differentiation of auxiliary equation. Now here 4 odd, this is 6, this is 0. Now continue the tabular form. Now you continue the tabular form. Now the continuation of tabular form is s square, which is nothing but 4 into 3, 12, 12 minus 6, 6 by 4. Now 4 into 2, 8, 8 minus 0, 8 by 4, 2, 0. Now s power 1. 6 by 4 into 6, 6 by 4 into 6 minus 4 into 2 by 6 by 4. Therefore, this is 36 by 4 minus 8 by 6 by 4. Now, this is nothing but 36 minus 32. This is 4 by 4 by 6 by 4. So, 4 cancel. Therefore, finally, this is nothing but 4 by 6. You know the same procedure, okay? This is 4 by 6. Now, this is 0. This is 0. Now, s power 1. Now, the s power 1, this is s power 0, x into 2, 2x minus 0 by x. Therefore, this is nothing but 2. Now, you already know that the last row first element must be a constant in the characteristic equation. The last row first element must be a constant in the characteristic equation. Now, then most of the students are having a wrong analysis here also. Positive, 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 positive. All the quotient in the first column is same sign. All are same sign. Now all the quotient in the first column should have same sign, and you treated the closed loop control system is stable. Wrong analysis, wrong answer, wrong approach. Why? Because this is the positive, this is positive, but from here onwards, this is not the original quotient. These are the quotients you can get it from the auxiliary equation. Am I not? These are the quotients you can get it from the auxiliary equation. So what is I am asking is, first you find the roots of the auxiliary equation, then you can have analysis is correct or not. Okay, first you take this one and we'll see the roots. Okay. Now we will see the roots of the auxiliary equation. Then whatever he is saying is correct or not, we will see. Don't decide it from the first column, because these are not the original roots. These are the roots you can obtain from the auxiliary equation. So now find the roots of the auxiliary equation. What is the auxiliary equation? Now here the auxiliary equation is, now the auxiliary equation is always even power of s term, s power 4 3s square plus 2 equal to 0. Can I say like this? Can I write like this? Y square plus 3y plus 2 is equal to 0, which means let s square equal to y. So what are the roots? Now y plus 1 into y plus 2 is equal to 0. Now see here, y plus 1 equal to 0, which means s square plus 1 equal to 0, which means s equal to plus or minus j1. Y plus 2 is equal to 0, s square plus 2 equal to 0. Therefore, s equal to plus or minus j root 2. Now, one pole is at plus j1, another pole is at plus j root 2, and one more pole is at minus j1, and one more pole is at minus j root 2. What I am saying? If the poles are symmetrical with respect to origin, now how many total number of poles? 1, 2, 3, 4. Even number of poles. How they are arranged? Symmetrical. In which axis? On imaginary axis. System is marginally stable. Therefore, the closed loop control system is marginally stable. The closed loop control system is marginally stable. Am I right or not? Now this is the closed loop control system. the given system is marginally stable. Now I think now you can easily understand. Now one complete row becomes 0 and I am saying system is marginally stable. The reason behind that is whenever the one complete row becomes 0, which means that is because of even number of poles. Even number of poles, there is a chance of arranging symmetrically on origin, sorry, with respect to origin, on S-plane, on imaginary axis, system is marginally stable. Understand or not? Then one shortcut method is also, sir, I don't know the roots and I don't want to do all these things. But without doing all these things, by looking the RH tabular form, by looking the tabular form, can I find the system stable, unstable, marginally stable directly? Yes. Now see, one shortcut method I am giving. If only one time, only once, if only one time the row of 0 occurs in the RH tabular form, only one time the row of zeros occurs in the RH tabular form, and second one is all the first column quotient should be positive. If these two conditions are satisfied, see, check once again. How many times the row of zeros occur? Only one time the row of zeros occur. And all the first column quotient, positive. If these two conditions are satisfied, and closed loop control system is marginally stable in a shortcut method. Now the closed loop control system is marginally stable. If only one time the row of zeros occur, and all the quotient in the first column must be positive. Previously I am saying same sign, but no same sign, no negative sign, all are must be positive, then the closed loop control system is marginally stable. So one point you have to be identified. Whenever the row becomes 0, which means that is marginally stable, that is a reverse second case. Whenever the row will become 0, in your mind you remember, oh, somewhere in the S-plane even number of poles, or somewhere in the S-plane the poles are arranged symmetrically. That point you should be remember, okay? Don't remember stable, unstable, marginal. That is the second, okay? Whenever there is a row of zeros occur in the RH tabular form, which means that somewhere in the S-plane poles are arranged symmetrically. Okay, that is the first point and foremost point you have to be remember. Because of that symmetrical poles, which means that the symmetrical arrangement is only because of even number of poles. Whenever the even number of poles are arranged symmetrically, then there is a chance of cancellation and there is a chance of row will become 0. Okay, no doubt.